So let us continue with the last part of this lecture 2 on AC power. All right. In last sections of this lecture, we introduced the concept of phasors, right? The phasor is basically trying to tells you the average value of the AC signal. Okay. So soon after knowing this average value or the RMS value, right? The other quantity that you should be able to compute in power system is the power itself. So when we say that the voltage drop across a certain equipment like an impedance Z here, so we have the voltage drop plus and minus V, and the current is flowing towards the positive direction of the impedance. That's what we call passive sign convention, where the impedance is consuming power to itself. Okay, so the concept of what we call passive sign convention should be known to you already from circuit. All right, that's why when the current is flowing into the positive terminal of a certain equipment, and we assume that this equipment is taking or it is consuming power. Okay, that can be called a load. So in this case, the UV, if it is an AC power, V is a sinusoid, and similarly, since this is the LTI system, so the I is also a sinusoid. So if we decompose, if we see what are the elements inside the C, so you know that the C is an impedance, it is an impedance, and it is a complex quantity consisting of R plus JX, where we have R as resistance and X as an reactance, right? And normally when we connect this voltage, we need to have, if we decompose this, we want to see what are the elements of Z. So if you look at the Z here, we normally model the C as the the parallel elements of R and X. Okay, so normally we put JX in this case, but never mind. In this case, we are still in the time domain function. Okay, so now you can see that since you put the time function of sinusoid for both voltage and current. Okay, so the power itself is also, it must be time function as well. So what's the definition of power? So power itself is the multiplication or the products of V and I. So the P here is also a time function, because V and I is also time function. All right. So let me rewrite this. Okay. PT is VT times IT. So the V and the I's are in time function. The multiplication, the products of these two are still in the time function, but it is in terms of power. Okay, this quantity is known in circuit as an instantaneous power. Okay, this is the instantaneous power, meaning that this is the power that is available at any instant of time. So this is a multiplication. So you have R and X. So everybody knows from the AC steady state analysis is that the current of the inductive current, or the current flowing through the inductor, it's 90 degree lagging the voltage. So that's why we have the V as here, and the IX is just lagging the V by 90 degree, or it is perpendicular to the V. Okay, that's why we say X is an inductive element, or it has the what we call lagging power factor. So the power factor we will discuss later. So, but since you should have done this in circuits, all right. But if you may come across the term power factor, okay, and the power factor angle is defined by the phase angle. So we have both lagging power factor and leading power factor. In this case, we're gonna talk about that later. So the characteristic itself of the voltage waveform, this must be known to you already. You have an R and you have X. So if you decompose the voltage and the current relationship of the voltage and current for resistor and for reactor, in this case, so there's this problem here. I mean, this picture here, the second picture, if you look from the second picture, you can see that the voltage and the current, okay, the two waveforms are in phase. So what do I mean by in phase is that there is no phase angle difference between the V. This is the V, or okay, this is the voltage waveform, and the current waveform is here. It is in the green, okay, in green. This is the green. Okay, so we say that the voltage and current for the resistor are in phase. In this case, are called in phase. Okay, as you see from in phase, as I said in the last lecture, the way we say whether it is in phase or leading or lagging, okay, we have to get the reference. For example, here we put 0 as reference. For example, here this is 0. So you can see that the green and the yellow, I mean the green and the red waveforms are at 0 at the same time instant. That's why we call this is in phase. Is it okay? So now we can say that you see for this is the picture 3. For picture 3, this is for inductor X, this is for resistor R, and this is for inductor X. Now you could see that the current flowing through the inductor is just lag the voltage. Okay, this is just to lag the voltage by 90 degrees. Okay, that's why if we say in terms of power factor, we say lagging power factor. Now you could see if you extend the current waveform, this is the green line over here. Okay, this is a green line over here. If you extend this a little bit, now you could see that the current or the green waveform becomes 0 at this time instant, and the current waveform, which is in the red one here, okay, just pass through 0 at some later time instant. Okay, so you could see this is the point in which the red or the voltage becomes 0, but you see the green one or the current just went through 0, or this is a reference line just right before the voltage, right? So that's why we say this is the lagging power factor. Okay, or is it correct? Sorry. If you say from here, you have to see it's not right. Okay, just forget about this one at this moment. You have to see the 0 here. Okay, this 0 here. If you put the reference, so the V here is just passing through the 0 line before the I, because I just happened at this point A and this is B. So the I went through 0 before after the point A. Okay, that's why we say Ix lags V. Okay, Ix lags to V by a quarter of this is a quarter, right? Because this is one period of the waveform. This is one period, and everybody knows that one period of the sinusoid is 360 degrees. Okay, and this is just a quarter of the period. So this is T by 4, right? And that's why this Ix lags the V by 90 degrees. right? This is I think this is clear, right? This is the voltage waveform, and the other one is the current waveform. Okay, so this is the VI characteristics of resistors, and this is reactor. So once we combine this resistor and reactor as an Z, or this is impedance, so you could see that R plus JX plus the I, okay, you plus the I and you multiply by the V. This is the product. Okay, the I here would be your IR plus IX, right? The IR plus IX. So now you can see that the P and the V and I just have a certain phase angle difference. Okay, the angle difference theta. But in this case, since we have the resistive part as well, the phase angle is less than 90 degrees in this case. So you can see that this is V and I. Since we have the reactor, so the I is just like the V by theta. Okay, from this picture, you can see that the I just went through 0 at this point, and the V went through 0 at this point, and I went to 0, passed through 0 at some time later, and that I mean that time difference is defined by the theta. Okay, that's why we say I lags V by theta radian. So it can be, if it is radian, then this is angle, right? Or you can change the angle into the time as well. Okay, that's why this is the angle difference. Multiplication of these two quantities, or I times V, you get this instantaneous power, or the dark line like this. Okay, so if you can see from this dark line, all right, you see this is a reference point. Okay, there is a reference point. The power here itself, it's, you know, we have discussed this. I think you should have discussed this in circuit already. You have the power. We don't have any separation between series and parallel connection. Okay, as long as you have the load. Okay, no matter how the loads, those two loads are connected, the power is the sum of all the power from each individual. I mean, from individual elements. So in this case, you have two components of the load called R and X. You have R and you have X. So the total power would be derived from the summations, or the summation of these two power from resistor and the reactor as well. So you could see the P itself is the sum of PR plus what? PX. Wait, sorry, this is the sum of PR plus PX. Okay, so PR is what? It is the product between V and IR, and the PX is product of between V and IX. So this, in this picture number 2, okay, the P is this P is equal to P times V times IR, and this P is equal to V times IX. So you can see that the dark line in the second picture shows the multiplication of V times IR, and the next one is P times V times IX. So basically this is PR, this is PX, if you want to put in this way. Okay, so now you could see that the PR has you know, when we find the average value, the average of this waveform, it's a certain constant value. Okay, so we have discussed this in class today. Okay, that the average value of a periodic function is derived from the integration, okay, of the area under the curve. So you could see that the integrate of this the dark curve here is non-zero, because the integration of this P is this area, right? So if it is becomes all positive. Okay, so if you have this integration positive, it is you know, when you average it, you just divide this by the period, okay, the length of the period. So this is becomes a certain number. Okay, let us denote as P. Okay, so when you look at the figure number 3, you see Px is equal to Vx times Ix. This is the power, instantaneous power consumed by the reactive components or the X components in this picture number 2. So now you could see that the average of this product, I mean the product between V and Ix, just got you know, pulsating waveform surrounding the zero axis over here. Okay, so that means that we have both negative area and we have equal positive area. So if we integrate, okay, if I integrate this waveform over the time period, okay, we integrate this over this time period, these two areas are just cancelled. Okay, so that's why when we integrate this, we find the average value of this product is to be 0. Okay, so by definition, when we have the resistive part and we have reactive part, right? When we find the voltage, I mean, when we find the power, instantaneous power, okay, the power consumed by the resistive part, it's always positive, where the average value, average power of the power consumed by the resistive, I mean the reactive part here, okay, the average value is 0. Okay, is 0. So you learn from circuit already that the average value for the resistive part or the real part, it's always called, you know, real power. Or we say then that is an active power. Okay, this is called active power, right? And the imaginary part, or it is Q, we call imaginary part, but imaginary part is more towards mathematics. In electrical engineering, we call reactive part. Okay, so the Q itself is the average of reactive part. Okay, so that's why we call reactive power. Okay, reactive part of the power we call reactive power. Okay, so from this definition, real or active power means, okay, the power in which, if we find the integrate, you know, and of the area under the curve, what's the meaning of the area? What about the I mean definition of this area? When you integrate P dt, okay, what is it, this element called? Okay, this is work, right? This is an energy. Okay, this is energy. When we have integration of P dt, you get energy. So that means that the this part, I mean the energy that going to the resistor, it's always positive. Okay, so that means that when we define this using passive sign convention, okay, that means that the power that is positive means that it is a load or that consume, right, that is consume power or consume energy. So in this case, okay, if we say from in this case, meaning that the this part, when you integrate this area, okay, this means that the active part, okay, or the P part here, it is the part in which we have real or active electrical work. Okay, electrical work. Okay, so this is the part in which you would get the real work. For example, when you put the electricity to drive a motor, or you put the electricity to light the lamp, right? So the part that produce the mechanical torque for in case of motor, that is the active part or active power P. and the actual power that give the light to the lamp, it is also active power or real power. So if you look from the English term itself, when we say active, right, active means that if a person is active, meaning that this person is very energetic and he has a lot of energy, okay, to do the work. So when we say active power, means that this is the power that give the actual or they give the real electrical work. Okay, that's why we say real power or active power. So reactive means that this part, the Q part, doesn't provide any useful electrical work. Okay, because once you integrate the area under the P, right, the Px, in this case you get you get 0. Okay, integration of the area under the curve, the dark curve of this figure 3, it's 0. Okay, so this is just to put you in the mathematical form. We call instantaneous power. From the first picture, we say that if V and I, this is V, okay, V is here, okay, this is V and I, you can see that I just lag the V by the angle of V, and you have the multiplication of V and I just like this. So you can see that the average of the instantaneous power, or small p, would take the value of Vi cosine theta, because the product of these two, you can see that the Vt would be the magnitude of V cosine, right, omega t, and this is angle of this, if you put this as a 0, so you put this as 0 angle, and this is the current just lag the phi, right? So you can put this is the magnitude of I cosine omega t, and the angle of I here is probably it is negative, right? If I'm not mistaken, this is negative of phi, because it just happened to be 0 at it can be sine in this case, and it can be either cosine or sine, because it's a sinusoid, right? So let's I will leave this for you to check, but when you multiply this V and I, you will get the two terms in this case, right? So you can see that for example, in this multiplication, you would see that the first part of this term, okay, the first part of this this is the multiplication of V and I. So the first part is pulsating around this line, okay, and this is the reference axis. So meaning that if you integrate the area underneath the curve of the first part I here, you will get non-zero. Okay, you will get non-zero power. Okay, so you can see either from here as well that when you integrate this in this part, because this is a time function, we plot this versus the time axis, or the omega t axis here. So you could see that the average of this guy, okay, this become constant in this case, Vi cosine phi, since this is a time function, all right, and the integration of this guy is 0. So the average value of the first term is this much. So that's why this is the average of the first term. This is an average of the first term. Okay, that is the Vi cosine, and this is the second term. Now you see this become constant as we discussed, because there is no because this is a time function. Okay, so when you integrate this part, this would become a constant. You can take out of the integration, so you get just something like this. So integration of sine over the one period of time, then you also get this term to be 0, right? This is 0. So when 0 times with any number, this would lead to the 0. So the second term, the plot of this second term is this line here. Okay, so you could see that for this line, okay, it is pulsating, or it is fluctuating surrounding this horizontal axis over time. So the integration of this is 0. So this is a part in which we don't have any useful electrical work, or to put it in a short way into the electrical terms. So the first part, the average power of the first part is called active power, active or real power. This is the power that gives you the actual work or the real work, right? This is produce real electrical work, and this is reactive power. Okay, or the average that you usually know. I mean, you know it already. This is called P, and this is directive power Q. Okay, so this is the derivation for P and Q. So this is the definition that you should know before proceeding to this course, right? Because we're gonna deal with power, okay? Because the course itself is power system. So you should be able to differentiate the difference between active and reactive power. What's the definition? So when we need to compute the P and Q from voltage and phasor current, so you have learned this already, right? The definition of which we will find this from if we have the voltage phasor V. In this case, this is a voltage phasor. Or if I use the notation in the course, I would put this as V and this is as I. Okay, and this is a complex phasor C. Okay, so generally the network elements in power systems are mostly reactive. So let us put the lacking or reactive element here. Okay, so V is here and I is here. So you can say that I lacks V by angle of theta. That follows the time the time waveform that we discussed earlier, right? You can see that if we want to compute the complex power, okay, or if you want to compute the P and Q that is delivered to this load. So by knowing this, the current phasor and the voltage phasor, okay. The definition of the power here, in order to determine the P and Q, okay, if you remember this correctly, okay, the definition of complex power is generally used because the complex power S consists of both active part or the real part and the imaginary part P plus JQ. Okay, to put in a short term, in a short explanation, okay, this is called complex power. Okay, and P is active or real power. Okay, and this is reactive power. Okay, if we want to determine this P and Q by knowing the voltage and the current phasor, so this must be V. If you know V and you know I, this the S can be defined. It can be computed from the voltage phasor times the complex conjugate of the current phasor, I conjugate. All right. Why is it conjugate? Because from this picture, okay, you can see that the VI cosine theta, the theta here, the phi here, if you look at the phi here, the phi itself is divided by the what? The voltage, the angle difference, the phase angle difference between two quantities, right? This is the phi. This phi is the voltage angle difference between V and I, V waveform VT and IT. Okay, from in this case, right? The phi here okay, this V, the cosine function here, okay, is an angle difference between V and I right here. So basically, if you see, to put it as a, you know, in general term, if V takes a, I mean, the phase angle of V is theta V, and the phase angle of I is theta I. Okay, so you can see that the phi itself is equal by definition of the theta V minus theta I. Okay, so the phase angle that you take inside the power calculation is the voltage, I mean the phase angle difference between V and I. Alright, so when we need to put this in terms of the power equation, so you need to put the, you need to have the angle, I mean the phase angle of theta V minus theta I. In order to achieve that difference between theta V and theta I, you can see from here that you'd have to put the complex conjugate to the to the current phasor. Okay, because if you take the V as V angle of theta V, and I, it is the current magnitude and the angle of theta I, right? So you could see that when you need to, when you do the complex conjugation at the I, so you get theta I, multiplication of these two, you would get V times I and the angle of theta V minus theta I, right? V times I conjugate, that would becomes Vi cosine, I mean phasor angle of theta V minus theta I. Okay, and the real part of this, we have you know, discussed this theta is equal to e to the j of theta. Okay, this is the angle, right? And this is cosine theta plus j sine theta, right? And that's why the V times I conjugate would becomes Vi, okay, cosine theta plus j sine, oh sorry, this should be cosine of theta V minus theta I plus j sine theta V minus theta I. Okay, so this is the complex power. So now you could see, okay, V times I is a constant, V times I times the cosine term, it is P actually. Okay, so this is the equation that you should know, or that's this equation that we will use it many times, I mean throughout this the whole curriculum, right? The Vi cosine theta, it's you know, it's an active power P, and Vi times sine theta, it becomes reactive power Q, right? So you so there is two possibility of, you know, having the active and reactive power to deal with active and reactive power. So in this case, if the current lags the supply voltage, if the current lags the supply voltage, if you draw the phasor diagram, this is V, and the current phasors is I here, right? So what is the phase angle difference between these two? So if you put V as a reference, so V, the angle is 0. So I, right? So for example here, this is the theta. So what is an angle of theta? So theta here is negative I, right? Negative theta, sorry, because you measure this from the 0 axis, right? This, and the you know, this angle is negative theta. Okay, so when you have the complex conjugate of I, this is I, right? I is equal to I and the angle of negative theta. This is V, and the magnitude of V, angle of 0. If I is here, your conjugate I conjugate will be here, right? With the angle of plus theta. Okay, now you would see this is the, in terms of the phase, I mean the phasor diagram of the, in the case of current lags the supply voltage. So the phase I mean the phasor diagram looks like this one. All right. So when we talk about the phasor phasor diagrams of V and I, it looks like this. So what about the product? I mean the product between V and I conjugate. All right. So when you have V and I conjugate, you see the product of this V and I conjugate is P plus JQ. Okay. So everybody knows that when we draw these two axes or the coordinates in the complex plane. So this is the real part, right? This is real axis and this is imaginary axis. If it is in terms of power, the real one is P, right? And the imaginary axis would stands for Q. Okay. So now you could see that the multiplication of V times times this I, okay. And anyway, when you have this, okay, your I conjugate is what? It is I and the angle of conjugate of negative. When you put the conjugation, you need to put the negative sign of the angle. So negative of negative become positive. Okay. Now in this case, right? You can see that when we put the difference, the multiplication of this, right? V times I conjugate, then you have what? V times I and the angle of theta here. Okay, so you have V times I times the angle of theta. Note that the theta here is positive, right? For this case, because if this is positive number, for example, I put this 30 degree, but actually it is minus 30 degree. Okay, note that the angle is the theta is greater than 0 degree. So when you expand this term, you get Vi cosine theta plus J sine theta, right? When your theta is greater than 0 or greater the positive angle, right? Cosine of positive is positive. Okay, cosine of positive sine of positive angle is also positive. So in this case, if the current lacks the supply voltage, okay, you get both positive part, positive real part and positive imaginary part. Okay, the positive real part is here. This is P. Okay, because reactive, the real part of this multiplication is called active power. So P is positive. All right, and the for this case, the imaginary part of this multiplication is also positive. So imaginary part of this is called reactive power or Q. Okay, so if I draw this, the product, right, in terms of power, you can also get the imaginary or reactive power to be positive as well. So we get Q like this. Okay, so in terms of this is a vector, okay, pointing from 0, and this is perpendicular towards the imaginary axis. So this is JQ. Okay, P plus JQ is S. Okay, this is S. Okay, and the angle of this guy is what? It is theta, positive theta, right? It's a positive angle. Correct. So by having the current lacks the supply voltage, then you get the Phasor diagram like this, and the power diagram. This is called power diagram or power triangle. To put it as a common term, this is called power triangle, because this is the triangle which represents power. Okay, in terms of power, we have active power, reactive power, and complex power to be shown on this triangle. Okay, so you also have another definition called if you say just the magnitude of this complex power, right? Or the magnitude of the complex power can be determined from the square root from the Cartesian, or the distance from the origin of this picture, right? The magnitude of which is P square plus Q square, right? The square root of P square plus Q square, according to the Pythagoras theorem, this is called S. Okay, the s here, when I don't put the underscore, would mean this is just a magnitude, right? So the magnitude or the magnitude or absolute value of the complex power is called apparent power. Okay, so this is called apparent power. Why is it called apparent power? So the apparent would comes from the verb to appear. Okay, this is to appear. This is the power that is supposedly to be, you know, available to the load, to appear to the load. Okay, this is the power that is supposed to go to the load. Okay, but due to the presence of reactive power, okay, this power is not going fully to the load. Okay, because the multiplication of V and I, you can see that if I want to get the apparent power, I could also get it from this equation as well, because this is the complex power, right? This is the multiplication of two complex numbers. I could put this as V times I, and the angle of theta V minus theta I. Okay, so the apparent power is also it can be derived also from the multiplication between V, average V and average I. Okay, so you know that the multiplications of V and I, it's a power quantity. Okay, so this is the whole thing. I mean, the total power that is supposed to be to go to the load, but this full power, I mean, this the 100% or the total amount of this doesn't go to the load due to, you know, the presence of reactive power. Okay, now you could see, you know from the definition already, that when you have both active part and reactive part, we already discussed that only the active part, or P, it's a part in which we get the actual electrical work. Okay, so that's why when we say the P, okay, we have the P can be defined by P is equal to V times I times cosine theta, V times I times cosine theta. In this case, right, if P is in, you know, is a V times I times cosine theta. Okay, and the whole thing, I mean, the multiplication of these two is S, right? This is, by definition, this is the power that is supposed to be delivered to the load, but due to the presence of the angle difference between V and I, okay, this power doesn't go fully go to the load. Okay, the actual power that would generate the real electrical work is P. Okay, what about the power that didn't go to the load? Okay, that is, you know, in terms of the reactive power. Okay, so this distortion, I mean this reduction from the power that is supposed to go to the load, that is S, and the actual power that generate electrical work, that is P. Okay, the ratio between P and VI, or S, okay, we call S, this is called power factor. All right, you know that the factor would mean that the 100% is 1. All right, if this power factor is 1, meaning that P is equal to S. All right, in case when the power factor or this ratio becomes 1, we in English term is called unity power factor. Okay, unity power factor. Okay, it's called unity power factor. When we have the voltage difference between the angle difference between V and I, the cosine, there is some value, right? You can see that when what is the in which condition we will get the power factor to be 1. Now you can say that, you know, you see from here the ratio between P over S, okay, it's cosine theta. when the ratio P over S is over sine theta, it's equal to 1. It only occurs when the theta is 0 degree, right? Theta has to be 0 degree in order to get this factor to be, the power factor to be 1. The theta of 0 degree would mean that the theta V minus theta I, okay, is 0. Okay, is 0. Okay, when theta V and theta I is 0, meaning that these two, okay, are in phase. Okay, so meaning that these two voltage and the currents are in phase. So you could see that when these two are in phase, V and I are in phase. You see, this is only happen when your load is resistor, right? We call when this condition happen, it only happens when your load is purely resistive. Okay, purely resistive, meaning that the whole component of your load just have only resistor. Right, only resistor. Now you see, when the current lags the supply voltage, meaning that what? You can see the angle difference between these two, theta V minus theta I, right? That would become positive, right? So the positive over here, you will see that the positive Q is positive, the theta is positive, P is positive, Q is positive, right? For this case, the power factor in this case, both P and Q are positive. This is the property of reactor, or L. Okay. Now, if the capacitive load or the current leads the supply voltage, you could see from here, this is V and this is I, right? Okay. What is an I conjugate? I conjugate is down below here, it's pointing downwards, right? Now you can see that the multiplication of V times I, you get the upside down triangle like this. This is P and this is Q for the power triangle, and this is S. So now you could see that the Q is becoming negative, right? Then it's negative because the sine theta here, okay, the theta is angle difference between V and I, okay. The theta V and theta I is positive, right? It's positive when you times by the conjugation of this, so it becomes negative. The sine of negative angle is negative of that sine. Okay, so the Q here, Q for the reactive power of the capacitive load is negative. All right. So from the previous definition, we have discussed that when the power is positive, meaning that the load is taking or that is consuming that is consuming power. Okay, I have written here is a passive sign convention. If power is positive, right, it means that this consume, or this is the load and it consume energy or consume power. So meaning that the Q, when the Q is positive, meaning that this load is taking or consuming that amount, that power, right? So in this case, this is reactive power. In this case, the inductor just consume reactive power due to positive Q, and the capacitive load just generate reactive power because the Q that we computed, it's negative. Okay, the computed Q is negative, right? So this is the summary of what we call complex power. Knowing the in this picture, you can see the power triangle, or in this case, this is a complex. Okay, sorry, this is for the inductive load. Okay, or in terms of power quantity, you will say that this is the lagging power factor. Okay, You should draw another picture here for the capacitive load. Okay, just draw it here. Or capacitive load, we say that the load here is capacitor, right? And in terms of reactive power, it would be the same thing. Okay, leading power factor, right? PF, this is power factor. When this is a capacitive load, then you get P. The P is always positive, and the Q is negative here. This is Q. Okay, this is S, right? So all these are known already, right? When we say complex power, we say the whole thing. We say the P, and we say the Q. The complex, I mean, this is a complex quantity of active and reactive power. Okay, active power, it can be real. Okay, it can be called real power. And since the complex power S, okay, is a multiplication between V and I, so the unit itself is VA. Okay, when we say just an apparent power or the magnitude of the complex power, it's also in terms of VA. And active power is W. This is the in terms of watt, and reactive power is VAR, volt amp reactive, right? Please take the great caution when we write the unit VAR. There are so many ways of writing this unit. Okay, if you look from the books, you can find many varieties, something like VAR, the capital V and the rest are small. You can see VAR like this as well. Okay, the correct ways of writing this, I mean, by definition, right? The correct way of writing the unit of directive power is this one. Okay, the rest is not correct. The rest are not correct. The capital V and the small AR, right, and all capitals are not correct. So when you write the reactive power, you should use this one. For example, when you write the kilo VAR, so everything is small. Mega is a capital, and VAR is small. Okay, giga, it could be giga as well. Giga, VAR, something like this. Okay, these are the equations that you know it already. Okay, and this is something to give you all the summaries, right? I think, yeah, as you probably know from any other classes, that when reactive power is associated with the electromagnetic field. Okay, when you have storage elements on in this case this is reactor. Okay, I'm saying reactors, it is very I'm sorry, it is very German term. Okay, but this is called inductor in English. Okay, I'm sorry, the previous names was not correct. So when we say when I say reactor means I'm saying in inductor in this case. I'm sorry, I'm very sorry, because today it has been long day already. Okay. Now you could see that there is a transfer of the power, right? In this between electromagnetic, that means electro is electric field, magnetic is magnetic field. Okay, when we use the L or inductor, right? It is the L is used to explain the magnetic field, okay, phenomena. Okay, so we have known it already that the P part is generating electrical work, and the Q part is producing doesn't produce any electrical work. So this is from the definition. When you derive for the trying to solve for the I from this differential equation, the first order ODE, which is this is the characteristic equation of this picture, Vt. right? And we're trying to solve the IT as a result of this. So when you solve this, this has been done in many classes, but that's why I don't want to put it here. All right, the results of this is written like this. You can see from this case, I mean from the slides over here, that when we write the v in this case, so we put the square root through in front. In many books is written like this. That is no surprise, you see, because you know it already, that the Vrms is Vm, or the magnitude divided by root 2. So when we put in this way, the coefficient before the sinusoid term, we generally use the magnitude Vm, right? So the Vm here is root 2 times the V, meaning that the RMS value is just the capital V, like this. Okay. When we write the time function, you have to, if you know the RMS value, you have to multiply by square root 2. But if you have just something like 100 sine of omega t, what's the average? I mean, what is an RMS value? The RMS is 100 divided by root 2. Okay. But if you were to know that this is the 100 RMS, so then when you write the time function, you have to get square root 2 times 100. Okay, that's just the technique. All right. So now this picture, we are trying to give you the electrical work, right? This is the rate of change of the work that is in the inductor, right? You see that the energy in inductor is a half Li square, and we put the I from the previous slides, and you find the rate of change of the stored energy in this inductor. You could see this is Q times sine of the 2 omega t minus phi. So twice of the omega, right? Omega t. So this is the psi function is pulsating over the t-axis, right, with the equal positive and negative part. So the average of this is 0. Okay, so it means that the rate of change of the store energy, okay, the energy of in the inductor changes, but the total rate of change is 0. Okay, meaning that it doesn't produce any electricity, I mean electrical work in this case. Okay. Now you could see from this example, when we have the L and C, as we discussed earlier, that the L is the representation of the energy stored in terms of the magnetic field, and the C is the energy stored in terms of electric field. So you know that in this circuit there is no resistor, meaning that there is no load to consume the energy, right? Meaning that from time to time, right, if Z is charged, the charge energy is from the inductor. When C discharge, right, this becomes source, and the L becomes the load. So there is the interchange between the energy of these two devices. So this is to show you that phenomena. Okay, we can derive that the instantaneous power at the inductor is this function, and the instantaneous power of the capacitor is this function. Okay, if we plot these three, the total instantaneous power, that is the total power that is delivered to this the whole sum of L and C. So it is a sum, the addition of these two. Okay, and you could see from here that when the sinusoid changed the sign, right? The sinusoid changed the sign when there is a 180-degree phase separation. Okay, so you could see that in this case, since you don't have any active element, or you don't have any resistor. Okay, by saying active elements mean the element in which it consumes energy, right? You don't have any active element, so the net or the average energy must be 0. Of course, it must be 0. Okay, as if we plot the time function in this case, okay, PL and PC just differs by the 180 degree, or it is in opposite, always in the opposite direction. If you see from PL is the blue line and the PC is a red line. You can see that PL and PCs are always in the positive in the different phase. Okay, and the summation of these two are called P. You can see in this case the peak is just different. Okay, when from this time period, I mean from this period of time, you see that the peak of the PL in this case is greater than the PC. So the envelope of the sum of the power just follow the PL, right? In this case, because the PC just subtract some parts out of PL. Okay, so now you could see that the envelope of P total just follow the envelope. I mean, just dominate by the PL. Now you could see that the sum of these two are, I mean, the average value of the total sum, which is in brown here, the average, since it is pulsating surrounding the 0 axis here, so the positive part and negative part is 0. Okay, so we observe that the the average power is 0 due to positive and equal positive and negative areas, right? So now in this case, you would see that the instantaneous, the change of sign in instantaneous power. Now you could see that when instantaneous power is positive, mean this is the load. And negative power, this means the source, right? So now it means that during this time period, period 1, in this case, the source, right, the L is the source, meaning that the energy, the magnetic field, magnetic energy here becomes the source, mean L discharge the energy, and the capacitor here, right, just is the power of capacitor is positive, means at this moment of time, at this period of time, the capacitor behave as a load of the inductor. Okay. On the other hand, in this case, right, when the power of L, the PL becomes positive, and PC become negative. In this case, in this area, you should note it yourself, meaning that in this case, the C capacitor becomes the source, meaning that capacitor discharge the energy, and the reactor just absorb the energy. So in this case, you see that the role of capacitor and inductor change in every half of the period. Okay, it meaning that it just charge and discharge energy back and forth. Okay. I think this slides it's all about the computing the three-phase quantity, three-phase complex power. I will do in the separate videos, and we will do this example, this kind of example in the tutorial session. So I think I conclude this lecture just for just up to this point, and we will see you in the tutorial. So thank you.